Martin Zeppenfeld. He will tell us about new approaches to high precision spectroscopy of molecules.
Okay, so thanks, Tanya, for the introduction. I really want to thank the organizers for giving me the opportunity to speak here, and in particular for organizing this great conference. I think a lot of us people have told me, and I have the same feeling, this is one of the most exciting conferences I've ever been on, and thanks to all of you for all your hard work to make so many great contributions. This is pretty exciting times for this field. So I want to talk a little bit about our work in this direction, on some kind of different ideas we've been pursuing on doing some precision spectroscopy experiments. Here's a brief outline of my talk. So I want to give a very brief introduction, just go over the motivation for why are we interested in precision spectroscopy of molecules. I will then also briefly introduce our toolbox we have developed over the last years for creating cold and ultra cold molecules. And then my talk will be mainly about three results. The first is to measure very narrow line widths now on electrically trapped molecules. A second aspect is to use light-induced fluorescence to do some nice electronic spectroscopy of formaldehyde. And then the last part of my talk will be on some fairly crazy new ideas on doing spectroscopy using Rydberg atoms and molecules. Right, so, I mean, why do we want precision spectroscopy? It's basically because you can really use the molecule as a toolbox to investigate lots of aspects of physics. Very well known, of course, is the search for the electric dipole moment of the electron. Also opportunities to look at purity violations in molecules. One could also mention looking into chiral molecules, looking at the differences between the right-handed and left-handed versions of the same molecules. Then there's, of course, the investigation of time variation of, I guess, what would then no longer be fundamental constants. Lots of opportunities to look at nuclear properties of the nuclei in a molecule, from shift moments, anapole moments, also looking for maybe for a nuclear EDM, and then also just lots of great opportunities to do comparison with theory, comparing with ab initio potentials, also just looking at nuclear coupling constants in molecules, testing molecular Hamiltonians. I hope I got everyone's favorite subject. Otherwise, let me know. I'd be interested in knowing any more possible applications. So there's really a lot of stuff we can do. I mean, so this is one of our motivations for looking into techniques to generate polar molecules at low temperatures. To do this, we've come up with a kind of unique set of toolbox of techniques. I mean, Gerd already mentioned this very nicely yesterday, so I just want to very briefly summarize this. The main part of my talk is going to be about other topics. But basically, all the people looking to generate molecules at low temperatures via direct cooling, you can almost always kind of distinguish between three stages of getting to low temperatures, which is an initial source, usually some form of deceleration, and then trapping and additional cooling. In our group, we have two approaches as initial sources of molecules. The second is the very well-known buffer gas technique, but I also really want to emphasize we have this great technique, velocity filtering. I would say it's definitely the simplest way to create cold molecules. And it's extremely robust. Of course, the other techniques have big advantages as well. And then in terms of deceleration, one big advantage here is we actually don't need any deceleration, starting with velocity filtering. Whereas, as Gerd was saying, we have our pretty awesome centrifuge decelerator in Munich to slow the molecules down. And then in both of these cases, we've now combined this with microstructured electric trap for basically collecting the molecules and holding on to them for a long time to do stuff with them. And finally, we've done various experiments inside the trap, in particular optoelectrical Sisyphus cooling, manipulating also the internal degrees of freedom. And again, what I want to talk about mainly today is now some nice experiments, especially in this setting, on precision spectroscopy. So, I mean, thinking about precision spectroscopy experiments, one key aspect is you want to interrogate your system, preferably for a long amount of time, in order to, not be limited by interaction time broadening. And here, kind of the ultimate point you can get to is to trap the molecules, if you really want to push interaction times to the absolute limit. Of course, it comes with a key problem, which is your trap is always going to lead to some broadening of your transitions. And in the case of electric trapping, if you reach a trap depth of 1 Kelvin, this basically means you're shifting your energy levels by 20 gigahertz. So this is pretty nasty if you want to do precision spectroscopy. However, we've basically come up with a 3-part solution to getting around this. The first idea is to make a homogeneous field electric trap. I'll explain that on the next slide. Then the second key aspect is to use a magic transition at a magic electric field. I'll also explain this. And the final ingredient is to then also cool the molecules to in particular, as we will see, this is essential to then also reduce Doppler broadening in our case. Okay, so, I mean, the first point, homogeneous electric field, I always say, this is kind of a complete contradiction, because if you want to trap something, you need inhomogeneous fields to trap it. But we've come up with a clever trap design to get around this. So the key idea is to use a pair of capacitor plates. I mean, this is the standard approach to creating homogeneous electric fields. And now the key aspect is to microstructure the surface of the capacitor plates. You have alternating narrow strips of positive, negative polarity. This creates strong electric fields near the surface of the trap, but they decay exponentially away from the surface. And then by adding an additional perimeter electrode around the outside, we get homogeneous tunable fields inside the in the central volume of the electric trap. This, of course, we demonstrated this quite a number of years ago. It's just an awesome device, gives us really long trapping times. The record we have is trapping times of basically a minute, and then basically observing particles, for minutes, as long as we're really patient enough to keep doing the experiment. So this is kind of the first key ingredient to get the homogeneous fields. And one thing we can also then do is to actually look at the real electric field distributions inside the trap. So you see very nicely you have this very large area in the center of fairly homogeneous electric field, and very strong high electric fields around the outside. And we've also been able to verify this spectroscopically. So basically what we're looking at is driving transitions in this volume rather weakly. And then the rate at which we drive the transition is proportional to the frequency at which electric field shows up. At least this holds in the limit where the molecules are relatively highly energetic relative to the fairly low fields we're probing at the center of the trap. And then we get this very peak distribution here. So the red is a simulation, the blue is an actual experimental data. They match quite well, and we see this very strong peak indicating this large region of very homogeneous electric field. However, you'll note here that, this is in electric field units, but for the transition we used here, this then corresponds to a half-width, half-maximum of 3.4 megahertz. This is quite nice, but it's kind of at the edge of what you might call precision spectroscopy, depending on your own interest, of course. So the question is, how do we get this even lower? And here the idea is to use suitable transitions. So whereas if we choose an arbitrary pair of states, the large Stark shifts in a normal trap would lead to gigahertz broadening, but again, we can reduce this to a bit over a megahertz using this specific trap. But now the key idea is to use transitions. This is a well-known concept, of course, from spectroscopy. We use transitions with similar Stark shifts. So basically, and not only with similar Stark shifts, but now use the tunable electric fields in the electric trap to set at a point where the two slopes of the electric fields are exactly equal. This is, of course, really nice about molecules. In many cases, things behave quite linearly, but the Stark shifts in molecules typically don't behave linearly at all, at least not over the full region. You sometimes get nice linear Stark shifts over a limited region, which means due to the nonlinearity, it's easy to find such points, such a magic electric field for a given transition for basically, I'd say for any polar molecule, and for lots of pairs of states as well. So it's really a very general approach. In the case of our experiment, we're doing this with formaldehyde. And here we're making use of the fact that formaldehyde is basically a symmetric trop, with a slight asymmetry. Which means it to a good approximation, it has the energy level and stark shifts of a symmetric top, which means that, for example, a transition from a state JKM 432 to 533 will have exactly the same first order stark shift for a symmetric top. However, there's now two effects which cause the stark shift to be nonlinear. First, because formaldehyde is not an exact symmetric top, there's a K doubling, which leads to a splitting of a few megahertz or so. And this means that for very low fields, the stark shift is initially quadratic. Moreover, at very high electric fields, we then get quadratic contributions as well due to coupling between neighboring J states, which then also leads to a slight change. And this means that there is a very large range where the stark shifts are exactly equal. And we can see this by just plotting the difference of the stark shift between these two states. And we see that for a field of 1 kilovolt per centimeter, we get a minimum in the differential stark shift. Also, something you could note is this is in fact a megahertz scale, despite the fact that the levels themselves are being shifted by about 1,000 times more. So this is really, even without going to this minimum, we're already dramatically reducing the shift. However, then really at the minimum, due to the small range of electric fields in the trap, we can, from the differential stark shift, we can simply again consider how often does each stark shift show up in the trap, and that's what we get here. So we see at this point the distribution of stark shifts is below 1 kilohertz. And so that really eliminates the problem to a large degree of the stark shifts broadening the transition. And that's precisely what we see when we do spectroscopy on this transition. So here we have 3 different spectra taking actually for different temperatures of the molecules. And we see that actually the fact that it's strongly decreasing really shows, at least at the high temperature, we're clearly dominated by Doppler broadening of the transition. We also have the red curve, which is a theoretical line shape, which basically just has 2 contributions. The first is the residual stark broadening of the transition, and the second is the Doppler broadening calculated from measuring the energy distribution of the molecules in the trap. And we get, so this is measured on a millimeter wave transition. It's at 364 gigahertz, so we get a relative line width of 10 to the minus 8. So the statistical error for the center frequency of this magic field transition is roughly 40 hertz, and we're currently still a bit busy with trying to figure out if we have any significant systematic errors compared to this value. So we're quite happy with this. It really shows, I think it's also the first time anyone's done this level of precision spectroscopy on electrically trapped samples. Maybe that's because nobody was crazy enough to try it in an electric trap before, but we're pretty happy that this works. Okay, so that brings me to the second point of the talk, which is electronic spectroscopy using light-induced fluorescence. This is kind of more of a side project because the main aspect for us is we have these nice experiments on molecules, but detecting our molecules is often quite difficult. At least it's difficult to do this very efficiently. So in the past, we've used the quadruple mass spectrometer for detecting the molecules. And this is really awesome in terms of it being really robust. You can switch to any molecule species very quickly and completely reliable. However, it leads to very low detection efficiency. And so what we've done recently is to set up a new detection system based on light-induced fluorescence. Specifically, this is for formaldehyde excitation via the X1A1 to A1A2 electronic transition with an excitation wavelength of about 350 nanometers. And then build optics around it to collect the stray light. Getting the set up was actually really a mess. We underestimated quite substantially the problem of suppressing a stray light. And there's several problems here. A big problem is that formaldehyde, it has the exact opposite of a diagonal Frank-Condon factor, so it basically never decays to the ground state. I think if the efficiency of going back to the ground state were the efficiency of not going to the ground state, then we wouldn't need any repumpers to make a mod. So this is probably on the level of 10 to the, I don't know, but 10 to the minus 4, 10 to the minus 5 seems quite reasonable. Instead, the fluorescence is going to all the other modes. Actually, the reason for this is quite simple, because in the excited state, the formaldehyde is actually bent. And therefore, you only have overlap with modes which are vibrating. And this also means that when it then decays, it's basically just populating all the modes available. And then the fluorescence is spread out over a wavelength range from 380 to 650 nanometers. I mean, in terms of detecting the photons, this is not a problem, but it means there's no chance of using any kind of narrow band filters to filter out your fluorescence light. Then also we have a very large solid angle. I mean, this is really awesome that we get up to roughly 70% in terms of getting a good collection efficiency, but this also means suppressing stray light is really difficult. We wanted to have a CW detection simply because our molecules are coming CW out of our trap, and we actually got this to work. Moreover, a key thing we underestimated is that all our optical components are fluorescing to some degree. So we were only able to suppress the light from the excitation later by about 3 orders of magnitude. After that, adding additional filter just had absolutely no effect. And this is also something we kind of underestimated. However, with a number of tricks, we were able to get the detection to work. Key aspects are a series of pinholes apertures for beam cleaning. So here, I mean, just using optical fibers might be a more standard approach, but at the high power levels, there's no commercially available fibers at 350 nanometers. To suppress fluorescence from our vacuum windows, we use uncoated vacuum windows at a Brewster angle. Then a key aspect is a series of in-vacuum apertures before and after the detection region. So here we have the detection setup inside. There's a pair of mirrors which collect the light onto a PMT, and then a large sequence of apertures. This is on one side, a similar setup. On the other side, just to block to clean the beam as well as possible, and then a kind of a final point to get to the really low level of background we needed was to insert some inserts to just block the edges of the mirror where most of the stray light was going. And with this, we were able to suppress stray light by an additional 6 orders of magnitude, and really got to the point where we're now more or less happy with the amount of background light, and we're really excited because we're finally back at the point where we can investigate the physics with cold molecules. Part of the process of getting the system to work again, we were able to do some really nice spectroscopy on the electronic transition. So this just shows a spectrum in the vicinity of the line we want to use to detect the molecules. And at the very first moment, we were actually quite surprised to find there were 2 lines here instead of just 1. Although this has a very simple explanation. So what we're doing, we typically, in our experiment, we end up with molecules in the state J equal 3, K equal 3. And then we excited this is a perpendicular transition to the J equal 2, K equal 2 state. And it's simply that this state already has a bit larger K-top doubling with a spacing of 37 megahertz, which is precisely what we see in the experiment. And moreover, we don't see 2 states here because we only have low field seeking states arriving at the detection simply because they're, trapped by electric fields before being detected. And then the real fun starts also when we apply electric fields. Then we suddenly see lines all over the place. We can do some fairly nice calculations of the Stark shifts via electric field. And in particular, as soon as we were willing to fit the excited state dipole moment rather than trusting the literature value, we were about one standard deviation from the literature value with a slightly larger error bar. We really get really nice agreement between the expected Stark shifts and measured Stark shifts. a really interesting aspect here as well is not only do we get J-state selectivity, which is one of the really nice things we have now going forward. I mean, our mass spectrometer was never state resolved, but we not only have J selectivity, but can even then, using the Stark shifts, really focus on individual M sublevels, which for us just gives us really awesome new diagnostic tools going forward. Finally, a second point is it was kind of fun to look actually at the lifetime of the excited state. Typically, for an electronic state, you would expect to kind of get a similar value across the board. However, a key point of formaldehyde is the excited state actually predissociates when you excite it. So for the state we use, actually only about 30% of the molecules decay radiatively, which is pretty good because there are states which are a lot worse. Because in particular, if we look here, if we look at the fluorescence coming off the state J equals 0K, so basically the rotational ground state in the electronic state, we switch off the laser at time equals 0 and see the decay of the fluorescence. However, when we use a different rotational state, we get a completely different decay. So I mean, if you're not familiar with these types of molecules, that can seem pretty exciting that the decay rate, the predissociation rate, which is causing the faster decay rate here, is completely dependent on the rotational state. Although, I mean, this is quite well known from literature, so this is basically across a various set of states, some literature values for the decay time as a function of the rotational state. You'll notice there's two different papers where they don't really always agree on which value is correct, and based on our measurements, we can say that the 1980 paper did a slightly better job of performing their experiments. So this gets me to the final part of my talk, which is investigating interactions between polar molecules and Rydberg atoms and doing various fun stuff there. And kind of the background for all of this is, I mean, here in the field of cold molecules, a key question is, how do we manipulate and control matter? In our case, molecules. And of course, people in the field are always very focused on using light for this process. And I mean, this has a simple reason, which is simply that it's been so successful using light to control atoms. Doing stuff, internal state control, cooling atoms, trapping, detection, spectroscopy, quantum gates, it's all possible with light. The key problem in the field of cold molecules, if you're not willing to go to molecules with diagonal Frank-Common factors, most molecules don't have optical cycling transitions, which means most of this is not possible for most molecules. And so then the question is, what are alternatives? And the key question is, can we use matter to control matter instead of using light to control matter? And of course, so basically using interactions between atoms and molecules, and of course a very similar system. We've heard a great talk on this, initially from the group of Pete Schmidt and also Didi Leibfried, where they do this quantum logic spectroscopy, where you're really using the ability to control atomic ions, to then transfer this control to molecular ions. And the question is, can we do something similar for neutral molecules? And for polar molecules, I would say the answer is to use Rydberg atoms, simply because, I mean, polar molecules, they have a nice electric dipole moment, and Rydberg atoms have a huge electric dipole moment. So if we just calculate the dipole-dipole interaction between molecules and Rydberg atoms, plugging in some typical numbers, so a typical molecular dipole moment might be 1 dBi, a typical Rydberg dipole moment might be 6,000 dBi, we get an interaction energy for a separation of 1 micrometer of 1 megahertz. Of course, this scales as 1/r cubed, so if we go even closer together, we're really at very large interaction energies between these particles, meaning this is really it's a great framework for getting very strong coupling between different systems. And it turns out that people have been thinking about this a little bit theoretically, so for all these different applications, of what one could do using light, it turns out for all of these there's proposals out there for how to do this using Rydberg atoms instead of photons. One key aspect to improve the interaction is to actually not just put your molecule and Rydberg atom next to each other and look at some kind of static interaction, but to use the resonant dipole-dipole interaction. I mean, we've heard this also just yesterday and I think also today in the context of molecule-molecule interactions, and it actually really works extremely well also for molecules and Rydberg atoms. So the idea is to have a molecule with a pair of states, J and J plus 1, and now choose a Rydberg atom with two states, R1 and R2, and the key ingredient is for the energy separation to be equal, resulting in resonant interactions. And in particular, this means we no longer need the particles to be in a controlled manner next to each other to observe interactions. We also, it becomes really easy to observe the interactions simply as the molecule and the Rydberg atom fly by each other, because if they start out in kind of the, one starts out in the lower level, the other starts in the upper level, then they can exchange the energy during a collision. And this is extremely useful, in particular, kind of at this stage we're currently in, where we simply don't have the extreme level of control where we can put a molecule directly next to Rydberg atom. I mean, of course, we're really getting there, but certainly for us, this is still quite challenging. And this really eliminates the need to get this high level of control. And in particular, it has allowed us to do some really nice measurements already just at room temperature. So the idea is to have a Rydberg gas and a molecular gas at room temperature. Moreover, we use ammonia molecule for the experiments. What's really nice here is that all ammonia molecules, basically independent of their internal state, have a transition at roughly 24 gigahertz. Due to the inversion, the well-known inversion splitting, and this means we also don't have to worry about the molecule being in different internal states. Instead, basically half the molecules will be in a given state. And so then we have the following experimental setup. We use a pulsed dye laser to excite Rydberg atoms inside a vacuum cell, and then state selectively field ionize the Rydberg atoms for detection. And so we have the following level scheme. We start out with rubidium in the 5s state, excited to the 46p state. And in this case, this is separated by 23.6 gigahertz from the 45d state. And what's nice now is that this quite closely corresponds to the inversion splitting in ammonia. And so we have an interaction time. One key problem now is that if we want to detect this change in state using state selective field ionization, that these two states basically have a very similar field ionization signal. However, by now including an additional millimeter wave pulse, we can very clearly separate the two pulses and get a very robust signal for this detection. So just as an example, here we have some data for field ionization. So we're applying an electric field ramp to field ionize the molecules. And in this case, for the, well, it's a blue curve, I guess, overall, we leave this millimeter wave pulse off. But if we now apply the millimeter waves, we get a very nice signal due to the ammonia, the transferring population to the 45D state. And we can also do this by just using different millimeter wave transitions to probe different internal states. And we get the following state map. In particular, what we see is that we only get energy transfer for the pair of states which is resonant with the inversion frequency of ammonia. We can also do this a little bit more thoroughly with a very nice aspect now, because if we have a Rydberg state, just applying a small electric field shifts a transition quite dramatically. And that's what's plotted here. So as a function of the electric field, we have the transition frequency between the NP and N-1D state, which shifts by about 1 to 2 gigahertz before it bends down because of level crossings from neighboring states. And by simultaneously changing the principal quantum number, we can continuously cover the entire frequency range, in this case from 18 to about 32 gigahertz. And so now we basically run our experiment having a transition which is resonant to any frequency within this range, and look at the amount of state transfer as a result of this transition. And what we see is a really nice peak here, exactly at the center frequency of the inversion splitting of ammonia. which basically, this is basically a low resolution spectrum of ammonia, where we're using Rydberg atoms instead of photons to probe the molecule spectroscopically. One interesting feature, just as a side note, is there's actually an excess signal here at roughly 30 gigahertz. And it turned out that we get a similar excess in signal when we repeat the experiment without ammonia in the system. And it turns out that this is a Purcell enhancement of blackbody radiation simply because of the 5 millimeter separation between the capacitor plates in the experiments. So this corresponds to the lowest order standing wave between the capacitor plates for electromagnetic radiation. Okay, so at this point, this is a low resolution spectrum, but what's really exciting now is the next step in the experiment, which we're currently starting to set up. So the idea is to combine cold molecules from electrostatic guide with ultra-cold Rydberg atoms in a MOT. And what's really exciting here is that this will lead to substantially reduced line width simply because, the line shape, the broadening of the line is currently due to time of flight broadening simply because the interaction time is very short. And at lower temperature, this can be reduced by orders of magnitude, which means instead of getting a very broad spectral feature, we would actually resolve the fine structure of the inversion splitting of ammonia, and basically get to a regime where we can really perform some precision spectroscopy on molecules using the Rydberg atoms. And I find this pretty exciting, and I think in different environments in particular, this might also be possible in supersonic jets. This might actually have real technological applications as well. And finally, the system is also interesting because we actually really are thinking of using the Rydberg atoms to detect our molecules. And in this setting, we can then use the setup to directly investigate the properties of such a detection setup. That gets me to the end of my talk. I'd like to thank the people involved in the project, so the entire molecule team, but in particular Martin Ibriga, Alexander Prehn, and Maximilian Löw are the students who have worked on the Sisyphus experiment where we've done the formaldehyde experiments. Moreover, Ferdinand Jarasch is my former master student who helped set up the Rydberg experiment. I want to thank Gerd Rempe where all this work is taking place, and thank all of you for your attention.
Questions?
You mentioned most of the molecules don't have a cyclic condition.
Yes.
So some molecules have close condition.
Well, in the sense of strontium fluoride and calcium fluoride, whatever, I meant those types of molecules. Yes.
Other questions? I had a quick question about the last part.
Yes.
When you detect using Rydberg atoms, you kind of get around the fact that your molecules are not cycling, right? But you still need the same number of optical fields to put the Rydberg to reach the correct Rydberg state and then detect optical.
Yes. So we're manipulating the atom with light and then manipulating the molecules with atoms.
So
right.
You don't cut back on the number of light fields that you really need, but
no, but yeah. Efficient. It's the same thing, I guess, with molecular ions. You're also using the light fields to control the atomic ion, and then using the atomic ion to control the molecular ion.
Sure.
Right.
Okay.
Yeah, I thought it was very interesting, sort of different kind of experiment. I was wondering if this would help with some of the theoretical understanding of the electron-molecule interaction. Electron molecule is similar to atom molecule. It's sort of tough thing to do, right? But the Rydberg atom is like, you have this electron sticking out, and so the Rydberg and molecule interaction, I think if you do careful theoretical analysis, should contain the information about the electron molecule interaction. So if by analyzing the experimental data, you can extract the electron molecule interaction through this kind of experiment, it would be very interesting.
So I think in the exact experiments I'm doing, this interaction is actually fairly boring because it's simply, you can probably get a very good result by assuming the molecule to be a point dipole and then having the electrostatic interaction with the electron. But something which is really interesting here, and for example, Fredrik Nacht is doing experiments in this direction, where he's using the Rydberg atom in his case, for example, investigating collision properties between an ion and a molecule, and you're just using the Rydberg electron to hold the ion in place.
Yeah. Those are sort of two sides of the story. It's simultaneously ion and also it's simultaneously electron.
Right. But this is fairly well known that you can really, in many cases, separate the interaction to really have either of these two cases. And then of course there's also other processes like the electron being captured by the molecule. And I mean, of course, in that case you get into more complicated processes. Which, yeah, I mean, it's actually quite well investigated at the level of using warm molecules and Rydberg atoms. So in particular, the experiments I showed, I didn't mention it here, but similar experiments were performed in the late 1970s and 1980s of seeing this resonant energy transfer. And I mean, the key novelty, of course, for us in this community, I would say, is that it gets really exciting at the low temperatures where suddenly you can also then use these interactions for quantum computation or quantum manipulation type of experiments.
So, yeah, very interesting. So this detection scheme, I guess it's just speculating, can you think of a way where it could be non-state destructive?
It is basically, well, it depends on your definition of non-state destructive.
Not destructive to the molecule. So like basically the excitation moves on to the molecule, to the atom. And that's
Right. I mean, the thing is, you can isolate the transition so that you know the final state. I mean, in principle, in principle, you do a state swap, right? But if you want to end up in the same state, which would be non-destructive, you simply then apply a microwave pi pulse afterwards to go back to the initial state.
Right, but if it's in a superposition of states.
Well, but whenever you detect a state, you're always destroying the superposition, right? So that's no cloning theorem. I mean, you can't get any more non-destructive than collapsing your wave function to the states, but still having the states be around afterwards.
Other questions? All right, thanks, Martin.
Thank you.